Hello everyone and welcome back to another Ghost Engine devlog. Before we go into the main topic for today, I want to make an announcement, or rather expressing the conclusion I arrived at, that for the last 2 or maybe 3 episodes I tested the idea of having music in the background. I will do work for Ghost Engine, but in the end I decided that I'll no longer do that. Okay, of course I will have music for myself to keep me focused, but for you, I want to give you the option to choose your own music to have in the background while you watch those devlogs. And at the same time, for myself, YouTube will no longer be picky about the music I am using in the background. Now, for today's topic, it will be a lot of things to cover because today is the last day of the first sprint. We will try to cover as much as possible of those user stories, and as you may have already noticed from the titles and the short descriptions here, it's about starting and hopefully finishing today the journey into the entity component systems land. And yeah, let's go with the first user story. Okay, for this one we want to be able to create entities, to remove entities, and to not get an error or crash when we try to remove or do some other thing with the entity that was removed. Okay, as usual, let's start by creating a branch, not tag, create branch, entity creation. Okay, now let's go to the code, and I want I don't know why. Oh, okay. I already created it seems. So what I've done, let me explain why I have Ghost ECS as a separate crate here. Well, it's actually something half-baked. Either let's delete this remnant of my sketches, most likely. So why I want to create it as a separate Rust crate? Because of 2 reasons. To create a game or a simulation of any kind, we are not always required to use an entity component system. For as long as we care, we might use simple arrays, 1D or 2D arrays, to represent our game state. And at the same time, another reason, I want you to be able to use the implementation of the ECS pattern we do here in other projects without requiring you to use GhostEngine. So let's go ahead and okay, we deleted that. Let's create that again. Okay, and as they are warning us, we also need to add that new crate here in the cargo file at the root of our Rust workspace. Ghost ECS. Okay, come on, my friend. Okay, save that, close that. We no longer need it. Now going to the root of our ECS crate. Let's go ahead and sketch out the things we want to achieve. An entity can be created in the ECS. Okay. Can create entity. Okay, another test. What was that? Can remove the entity. Okay. Can remove. Okay, I can't type. I think I have some allergies or some other stuff because I don't know. I was walking a little bit outside, and since I was doing this little work, and since I came back, my eyes are, I don't know, like someone pepper sprayed me. So can remove. Come on, can remove entity. Okay, and the other thing, if we try to remove an already removed entity, there should be no crash or error. Okay, this requirement will be covered by this one. Can remove. No, we actually have another test. So the first test about removal is can remove existing entities, and then can no don't crash. Come on, don't crash when removing unknown entity. Okay, let's delete that. Now we need to think a little bit who will create those entities. But before I go into that, let me switch to my drawing board. Okay, let's ignore that. We'll arrive at that subject in a little bit. Let me get a new layer here, and I want to use this color. Okay, so the architecture for our entity component system implementation is, let's say it's a naive one. It will not be the most performant one, but it will allow us to represent application state using ECS. You will notice the shortcomings of this architecture while we go explaining it and implementing it. So our ECS will have those things. So at first we will have a bucket. The concrete implementation doesn't matter. We'll have a bucket where we will store our entity IDs. entity IDs, and let's go and give some examples. Okay, then we'll have for each type of component we can add to an entity, we'll have a dedicated bucket. So we'll have those buckets for components of type T1, and here we will have instances of this component T1 1, T1 2, T1. Okay, let's go with the 3 here. T1 3, and for type 2 something similar. T2 1, T2 2, T2 3, and so on and so on and so on. For Tn we have a bucket with Tn1, Tn2, and Tn3, and so on. And those are the components. Now, one thing you may notice, and this is part of those drawbacks of the design we will go ahead with. If we don't have component of some type for an entity, what we will have, because if you look here, you will say, okay, I have all those components for each entity. And by the way, how do I know which components are for which entity? So each bucket stores a component type, and each column contains not n but 3 here. Okay, so each column here contains the components for a particular entity, and you will notice here, I'll try to highlight it like this. So this goes with this. Okay, and let's try another color. Let's go with light blue, like that. I hope, okay, it's visible. Okay, I'll highlight it like this, this. Okay, and whoopsie. I hope that now it's clear how we make the link between an entity and a component. So let's go again. We have a bucket of entities. Most likely they will be integers instead of unique identifiers. I will describe a little bit the difference between those two, but first let me finish the sketch here. So we have those entities, then we have buckets for each component type, okay, and we know which components are assigned to which entity because we have this entity ID acting like a identifier for the place, not that color, this color, for the place where inside component of type T bucket, this one on this entity ID will also give us on which position we have that that component. Now you may ask what happens when you have something like this. Let's say for entity n, dots entity n dots entity n. So let's say for entity n, we don't set all the components. Let's say for entity n, we set only this type of component. In this case, we need to have a way to differentiate between having a component and not having a component. And instead in those cells in each component bucket per type, we'll have an optional. So we'll have an option. We'll have an optional of type T1. Okay, T1. Null T2 and optional of type Tn. Okay. With that in mind, you will notice that if we don't set component T1 and T2 for our nth entity, those will be, let's say, empty. Let's just do some cross-hatching to represent the nothing, none variant, and we will have an actual value here. So this space is wasted, but implementing the storage for our ECS in this way will make our life easy. So I rather go with an easy implementation. Go ahead and use the ECS in different scenarios, and when we notice performance issues, we'll go ahead and redesign this in some other way, more performant way, rather than trying to think from the get-go what will go fast. Yes, we might go with theoretical ideas. For example, here, like, of course, it will be faster on modern CPUs to have continuous memory buckets instead of each component instance of type T1 to be in different regions of the memory. Okay, and of course somewhere here we have our query slash system. Okay, if I can write systems part of the equation, but for now we won't talk about this. For now we'll just focus on those two, and in the current user story especially this one. Okay, now coming back to the code here, you see, can create entity, can remove existing entity, can don't crash when removing unknown entity. So who is creating those entities? Coming back to this sketch, you would say, okay, the ECS as a data structure will give my entity. So this, well, not necessarily including the systems. Let's better go like this. The dotted line. Done. So this will give me creation, deletion, some other actions for entities, components. Okay. With this in mind, we need to name these systems somehow. From the implementations I studied, the literature I followed, usually they call this the world. So this is a world. Personally, I would rather go with a universe. I would rather go with this terminology, but well, I have the sense that the world is limiting when the universe is infinite instead of limited. So in our implementation, I will go with this terminology. Okay? Now, going back to our tests here, what I want to make sure of is that we can create default universe, okay, and universe default. Perfect. Of course, if we go ahead and do cargo test which project, I can't type. Today is not a good day for typing. Ghost ECS. If we do that, of course it will fail because we don't have universe defined. So let's define it. Public struct universe with no fields for now, but we want it to be, oh come on, not the bar but default. We want it to be default constructible, and we want to import anything from the parent module. Okay, so yes, those three failed because yeah, they are not implemented. The tests themselves are not implemented, not even the thing, the actual implementation that we are testing. So let's go ahead and take care of the second test, can create entity. And as we mentioned here, this universe will, oops, to the code, this universe will create entities for us, assign components to an entity, remove components, yada yada. So let's create a universe. By the way, if you think that it's bad for us to use the universe terminology when the other implementations are using the world terminology, let me know in the comments below, and let's have a little chat about this. And yeah, maybe we'll go with the word terminology too, but that's a small issue. So we have a universe, an empty universe, default universe. Default doesn't really mean empty, but yeah, in an initial virgin state. And then we want to get for ourselves an entity from our universe in this way. Come on. Universe dot create entity. I can't type. I don't know what's happening with me. I'm taking lessons for the touch typing, but yes, my typing improved in the last weeks. Yes, the last weeks, but sometimes I just go nuts with my typing. Okay. After we create this entity, we want to check that this entity actually exists in the universe. So for that we will assert that universe dot how should we call this one? Exists. Exists. No, I will be explicit. Entity exists, and I give the entity as an argument. Okay, so let's go ahead and implement those. Let's have an implementation block for universe, and first of all we have not a default, we have a function create entity. Of course this one will mutate our universe, so a mutable reference to self, another argument, and it will return an entity. Okay, it will return an entity. Good. So this we'll see how this is done. And the other function it's called entity exists, and for this one we require const reference to the universe, and this one is a boolean. Nice. Now let's talk about what an entity is, and if you recall This note from the user story: research the feasibility of using UUIDs for the entity ID instead of incremental integers. And what I had here on our where's the pen? What we had here on our drawing board was this. Let me zoom a little bit. What I was brainstorming here, the advantages and disadvantages for both unique identifiers and incremental integers. And what I was doing here was basically this. Let's consider that we have two separate universes, okay? Universe 1 here and universe 2 here. Now, with those, if we go with incremental integer, in each universe we will have some entity ID counter or last used entity ID, so that when we create an entity in the universe, the entity will get its ID with the formula the current entity ID current plus 1. Okay, so we created an entity here with ID 1 because we had no other entities. And now in the second universe, okay, we start from 0, then we go to 1, and then we go to 2. And this is our current value. And we created those two entities here. And later, at a later time, we want to merge two universes. Think about like this. I have a big map. I have a big map, and I can't have that big map in load it in memory. Think about an open world game like Red Dead Redemption or Oblivion and so on. Instead of loading that monstrosity in our memory, we just load chunks. Okay, and each chunk might be viewed as an universe. So when we merge two universes together in a single universe, we might have conflicts while merging. Okay, for the entity ID counter, we solve the conflict by just taking the maximum between the two universes. For E1, because it exists in both universes, we don't know what to do. Okay, that for E2 it's straightforward and okay, because this E2 exists only in the second universe. So we need to somehow differentiate between E1 from here and E2 from here. Way would be, instead of trying to merge and reuse the content of the second universe, instead of using this, those will actually be copies. Okay, and if we go with the copy way of doing things, we will have this. We will have our merge universe, and we copy. Oh, come on! Why you? Okay, you are working in it. So we copy what we have from our first universe. So the entity ID counter starts at 0. We create E1 1. This one goes to 1. Then we are done cloning stuff from the first universe, and then for the stuff in the second universe we go, okay, there's an entity into 1, so we copied this one. Okay, 2, bear with me. Then we copy A2 from the second universe, from the second universe with ID3. Why ID3? Because we have this entity ID counter. And now we have our merge universe. If we go with unique identifiers, there is a really small chance of getting the same unique identifier. We will look in a second of how unlikely that is. So in that case, entity 1 from universe 1 is different from entity 1 from universe 2. But the disadvantage is that with incremental integers, we will use 31 bits on, not 31, 32 bits on 32-bit architecture and 64 bits on 64 bits architecture. So for incremental integers, the memory usage is a word per entity ID. If we go with unique identifiers, we have 128. Let me double check. Yeah, this one. So where are you? Yeah, so we have 128 bits for each unique ID. That means 2 words. I hope I'm not butchering the terminology. And the probability of getting a double unique identifier is collisions here. So the number is this is the probability, and the number is equivalent to generating 1 billion unique identifiers per second for about 85 years. So we have no problem. But they are yes, they are requiring 60 bytes. So coming back to the other sketch, this one. Come on. Oops. How do I reset? Ah, here. Okay, perfect. So if we go with incremental integers, our life will be easy when doing this indexing from an entity ID to an actual component of that entity. If we go with unique identifiers, we'll use double memory or 4 times more memory depending on the target platform, and you won't be able to use the unique identifier to get those components from that particular bucket. what we can do for that, we can have a map. Can have a map that maps from UUIDs to an ID. But in my opinion, this is much more work than going with this idea of copying the entities and the components from the source universe to the destination universe. So yes, we decided we will go with incremental integers. Let's put a note somewhere around here. Incremental integers as entity ID. I want to put this on the sketch too, because I don't have, if I don't have it in front of me, I might forget. And we also go here in our user story and conclusion, if I can spell it correctly. Conclusion, we go with incremental integers. Okay. Oof. Why this is happening to me? I don't get it. Okay, and let's go to the code. Okay, so we need to have some static counter for our universe. And to be honest, I think I have to declare it outside of the universe struct. And public, no, this one should be internal. So if this is declared outside of the universe struct, so if this one, if it will be declared outside of the universe struct, then we will not have this problem with having the entity ID counter inside here and synchronizability in there, because if we have it declared here, entity ID counter, if we have it declared here outside of the universes, and let's say we start from 0, when we create entity 1 here, it will take this number plus 1 as the ID, so this goes to 1. When we create this entity, this actually will get 2 as the ID, and this one as 3. Okay, and let's suppose we create another entity in another universe. So we create it and we assign ID 4 because we have this. Okay, nice, I like that. So let's try to define it. And this must be static something, static entity ID counter, type usize, and the initial value should do, well, usize is unsigned. You know what? We'll change a little bit. We will actually, and this is not entity ID counter, it is next and entity ID counter. So we start from 0, and first we create the entity with this ID. Here we define. What did I do? Oh, I moved the coding window to the wrong no workspace. So we first use this ID as the entity ID, and then but it's not good. It's not good because if we come back to our sketch, okay, I'll use the mouse because I'll just show something stuff I will not draw. So we have this part per universe. If our next entity ID counter is defined outside of the universe, that's bad. Let's ask Rust. So Rust, no, not a standard library. Rust define a static field in struct. Okay, nice. Nice. Well, but this is a const. You can declare field static in a struct. You can declare a static variable at module scope. Exactly how we started. Not nice. Maybe they changed something. Let's try our luck. We have our start, we have our implementation block, and let's go like that, and it will cry. It will cry because the static items are not allowed. Damn it. Because if we have it outside of our universe, when this, not this sketch, so if we have this entity ID counter outside of the universe, when we assign IDs, like this one, this will be number 4. We'll have index number 4. So the components for that entity will be here somewhere instead of starting here. think. You know what? Actually, instead of having it as a static, I'll declare it as a field of the structure. So next entity entity ID will be a new size. Okay. So that will be a new size, and here when we create the entity, we will just return entity with ID self dot next entity ID. And ID equals that, and we do that +1. Okay, let's define the entity. I'm tempted to actually just use a type alias. Entity, that's an EU size actually. So type entity. What's wrong here? We just return ID. Okay, fair enough. Fair enough. Now entity exists. We need a way to store those entities. Do we need to store them, or it's just enough to compare the entity we get as a parameter here? We get an oh, come on. What's wrong with me? So we get an entity and we want to ask the universe, is this entity defined? So we have this next entity ID. We have that. And yeah, we need to keep track somehow. We need to track them somehow. Let's just go with buffer for them. It will be a vector of type entity. Or should it be entity ID? Yes, okay, and after we created this, we also want to add it to the entities and in the entities buffer. We push over new ID. and we return that ID. Okay, let's go with entity ID here. Okay, so we have this entity ID, and we ask ourselves, we ask the buffer entities that contains, and we check if it contains our entity ID, and we just return that, right? Because it is a boolean. Okay, so that's that. Okay, we need to define this as mutable, and let's compact the test a little bit. Now let's check that stuff out. So we passed the creation tests. Okay, now can remove existing entity. We'll just copy paste this. Assert. Okay, so you have our universe, you have our entity, and then we ask the universe. Oh, not universe, but universe needs to remove entity. So we remove the entity. So we remove the entity. We remove the entity, and then we check that entity does not exist. Okay, so let's define this. What? Create entity exists. Oh, yeah, right. This is remove entity, and we generate that and jump to it. We move it close to the creation. And for this, I think this is a little bit tricky. We don't return anything. It is a little bit tricky. We can go ahead and just rename this entity ID. We can go and ask the entities to remove so remove, delete. Sorry. Oh, come on, reverse, retain, remove. Okay, so for this one we need an index. Okay, let's get you an index. Actually, yeah, let's find the index. So let entity just index equals so self dot entities dot find text. Yeah, yes, so We don't have find. We don't have find. Curious. Position. Okay, first. This gives us an index. Oh, come on. This is weird. Oh, iterator. Find. Okay. Position. Yes, this is what we want. Okay, so the predicate here is this. Our x must be equal to the entity ID we have there. Okay. Okay, we'll deal with that. So this one is an option. So if let's index equals index, so if the entity actually exists there, we remove it. Get rid of that. And what else? This. Okay. And yes, this must be mutable. And I guess we are done. Let's test. Okay, we can remove an entity. Nice. Now let's implement this one. For this one, we have something similar with this. Okay. And for this one, instead of using this one, actually, you know what? We don't even need an entity already to exist in our universe. We just want to remove something that has ID, I don't know, 9999. And we check. No, we don't need to accept anything. We don't want to crash or do some weird stuff here. Okay, so let's test that. Nice. Now let's go back to the user story. So now we can create an entity. An entity can be removed, and if we try to remove an already removed entity, there should be no crash. Perfect. Now, before I commit the code, one thing I want to do is to run our full checks. Okay, they are passing. So let me commit the code. Okay. We stage everything, and we also stage this cargo file. Yes, and yes. Okay, so this one is about engine PCS. Create and remove entities. Nice. We commit that. Actually, you know what? I won't create pull requests and so on, so I'll amend this if I can. Yes, I can. So I'll amend this with close this number 6. Close this number 6. Okay, perfect. And I'll switch to checkout branch develop, merge branch, creation, entity creation. Nice. Merge. I think I'll activate the always do create a merge commit. Okay, so I'll delete this branch. Actually, I will not delete it. Instead, I will rename it. Rename branch, this branch to 7. And for a 7th user story, this one. Ooh, no, in the milestone view. In the milestone view, we have this. Add the possibility to add plain data object as components. Okay, so this is basically about this part. And each component type should be placed in its own memory continuous bucket. Yes, those. Type 1 will use this memory bucket, type 2 this memory bucket, and so on. Next, when an entity is removed, the corresponding components are also removed. Okay. The memory buckets must be compacted when components are removed. Oof, yes and no. We have to take a decision here, because if we are not compacting, we will use this idea of a component might be there or not. So each cell in our bucket will be an optional. But if we do compacting, let's say we remove entity 2 here, so this column will go away. Oops. So this column will go away, and everything after that will be moved. Now this might take some time, but at the same time, when we will iterate over our buckets, we'll have continuous components. We'll not have component, gap, component, and so on. But if we do that, we need to keep track of, again, we arrive at that problem. We have an entity ID, and we need to somehow track the actual index in the bucket for that entity ID. We'll not go that route. We'll go with this optional elements in the bucket, because it's much easier to implement, but yeah, it might not be the fastest thing to do. Oops, here. So this one, let me edit. Memory buckets must be compacted. No, we actually won't do that. And let's mark it as done, because if you don't do it, it is done. And after compacting the memory buckets, the link between, okay, this is also, you no longer do it because of the design decision we took. And we will concentrate on those two. So each type should be placed in its own memory continuous bucket. Basically, what we want is this. To test this scenario, can add component to entity. And for this, again, we want an universe. And we also want an entity in that universe. Okay, we want this entity, and then we want with the universe to add a component. A component of type useSize. I don't know, I just like this type as a dummy type. So we want to add this component to this entity. Okay. Okay, you have this weird syntax. Next. And then we want to assert that the entity has the component. So assert the universe has component of type useSize entity. Okie dokie. And now, when I see this, something comes to mind. I don't think I have to draw this one. Let me try to explain it. So, well, let's at least reference this drawing. So we have those buckets for each component type. In this particular case, we have a component of type useSize. So T1 is useSize now. Well, let me use the pencil because so this one is useSize at the moment. useSize, okay. But for this entity, we can only add one component type. Let me rephrase. So for entity E1, we can add only one component of type useSize. And then you might ask, okay, but what if I have multiple components that are actually useSizes, like the health, the distance traveled? Okay, those are more likely floats, but details. In that case, what we might have, I guess we already did something similar with the resources. You see here with the resources, I'll go to the tests. So add, we have this idea of adding a simple resource, which is a new size, and an object resource, which is a struct, basically, in Rust, a struct or an enum. And we can use the same idea of wrapping floats inside the struct to be able to differentiate between two floats. So we will use the same mechanism for our components here too. So can add simple component entity. Okay, then can add object component entity, and for this one I'll not use a usize but the same stuff, struct speed and offload, and we'll have speed here. This one, those two are speed. Okay, now that we have our two cases covered, let's implement. Okay, add method, and ooh, we don't like that. So create entity, remove entity, entity exists, add component, move it here, add component. We need to take a generic type T. This is the entity ID. Oh, come on. Did you generate two sizes? Entity ID, okay. So when we add this component, we want to add it to the correct bucket. And how do we identify a bucket? We'll identify it based on the type ID. First thing first, I will compute the type ID. So not std, type ID of what? Of our type T. Okay, so we have the type ID, and what don't you like? What? What? And I don't think we need to return something from this one. So what's wrong here? The parameter T may not live long enough. Okay. So let's do a static bound for T. Okay, let's go with that. So we have our type ID, and we will use a hash map to get from a type ID to a bucket. So let's go to the universe and create here type buckets. No, components. Let's go with components. And this will be a hash map from a type ID to actual, well, not, we can't target here. If we go like this, we need to parameterize universe. We will do again something like we did for the resource manager with the resource trait, this kind of stuff. So here we will have a boxed what is this? This is component bucket trait, and we need to mention that. So let's define this trait. Should this be public or not? No, let's define it as private, and we'll see later. So we have this trait. Remember the design that each cell here is an optional. Here. So we want something like push none, immutable reference to self. We want to have that, and we want to implement component bucket trait for vec of type T. Okay, so we parameterize the implementation but not the trait. Perfect. And we go like that, and we do self dot push none. Push none. But we can't do that because we have a vector of T's, but we want a vector of option T. Okay. Next on Dallas. So this one goes away as component. So we have the type ID, and we'll go like this. We'll go to our components, and we will not push, but insert no, first thing first, we will not has contains. Yes, contains key. We first check that we have no, you know what, actually wait a second. When we create the entity, referring back to this drawing, when we create an entity, we want to go and initialize those components to nothing. Okay, so when we do that, so we save the ID of the entities, and we do self dot components dot no, components. If I do for A and self dot components, what type ID? Okay, so I get the top, so I get type ID and type ID and what? And bucket. I get the type ID in the bucket, and for any of these, do I need the type ID? Not really. No. When I create an entity, I want to push on an uninitialized components to all buckets. But what happens? Okay, here for each, yeah, we can ignore that. For each bucket we want to push none. So this is perfect. Components. Not. Okay, I think that's good. Next, when we add a component, so when we add a component, let's say we add tn at the moment. So this bucket is not initialized. This bucket is not initialized, but we want to initialize all cells here with uninitialized components of type n, and set the component only for the entity you are interested in, only for this entity. Okay, so yes, we check if the key exists. We check if the key exists. So if that condition holds, so if the key exists, we just do the components that get mute. This borrows the key, which is the type ID, and gives us an optional. Okay. So if some bucket L, okay, I'll call it that. If bucket cell, if we have a bucket cell, we want to set bucket and here we need if let. So you want bucket cell to be set to the instance of t. Okay, and we will require t to also be default constructible with a static lifetime. And we need to box this one, right? Expect to... Okay, so let's box this one. The trait bound T component bucket trait is not satisfied. Required for cast to an object typed in bucket trait. Ooh, wait a second. Wait a second. We can... yeah, so this one is not the bucket cell, but the bucket. This is the bucket, and with this bucket, we want to downcast it to the actual type. So let's steal again from what we did with the resources and have those two. Or is there something better? Should we require T to also implement any? No, I don't like that. I'd rather have our component bucket trait force us to implement as any and a mutable variant. Okay, and let's implement missing members. Self. Ooh, and no. Here we need any, and here we need mutable reference to on any. Okay, go away. We need to import any, right? Right. Okay. And the returns. Okay. Immutable any and constant reference to any. Where are you? Any. Okay. What's wrong here? Oh, right. So I have that, not that, and that. No. Segmentation. So I select that. No. Aha. I told you I want to get proficient at using the keyboard. And when you learn, it's like, whoa. So I want that. I don't want that. I want that. Next. I don't want that selected. I want that selected. Not that. And that. So with this, we just go like that. And like that. Okay. Dynamic. Oh. Okay, I lost time for not seen but been. Oh, god damn it. Mutable. Dynamic. And dynamic. Mutable. What do we have here? Not all trait elements simply missing as any mute. Oh, correct. Okay. And what's wrong? The parameter may not live. Okay. So we want this to be with a static lifetime. And what else? Syntax. Oh, it's the other way around. Okay, next error here. So here we have our bucket. We want to go as any, and this is mutable, right? Right, this is mutable. downcast mutable to a vector of type t. If I can just do that. If let's bucket equals to that, so the downcast might fail. It shouldn't, but it might fail. So if it fails, we do nothing. But if the downcast succeeds with this concrete bucket, we want to go to that bucket and not first find iter, to use a mutable iterator to find replace, no, to find, and we need a predicate, so we want to no, we don't want that. We want index mute. Okay, performs the mutable indexing container index operation, and this might panic. Okay, let's hope for the best. We have our bucket, our index mutable, and our index. Our index is the entity ID. Okay. So let's get that and plug it there. And with that, I want to set that to none. What? Cannot assign to this expression. Okay, so let index. Okay, but what if I do this sort of stuff? What's wrong? Expected due to the type of this binding. Yes, size option. What did I? Oh yes, this is an option. Option T. Okay. And yes, now we can set the component not to none, but to the default value of that component. So some default. Okay, and what's not to like here? Cannot borrow self as mutable. Okay, this is fair enough. What next? Okay, so we treated the case when the component bucket exists. It does not exist. We want to do self.components.insect, and we have our type ID we computed above. And what do we want to insect? We want to insect a vector of optional these with capacity. No. Option, okay, back with oh, yes. Come on, with capacity. Not a good day for typing. So what's wrong here? Oh yes, this little fella. So this function takes one argument, but yes, the capacity itself. Capacity. Okay, let's compute the capacity. Capacity equals what? Our num. Yes, it equals self.entities dot count. Line. Yes, this one. We want that, but then we don't like something. And what is that something we don't like? Oh, we need to box this one. So if this is a new bucket we need to create, we reserve ourselves this much based on how many entities we have, and then we set the component, not insect. This one is not with insect, but rather yes, we insert the bucket, and inside that bucket we can actually go and extract this one from here. Bucket capacity, let bucket equals that. So bucket entity ID equals this. I think we can simplify this, but for the time being I'll leave it like that. This must be immutable. Yes, that must be immutable. This seems okay. Now let's go to the errors. That component, the thread bound speed. Okay, let's define. Derive, not define, define default for speed. And now what we need to implement is this has component method. So has component, no. Component, add component, and we'll just duplicate this one. Call it has component of type T. That's default constructible plus static lifetime. Okay, it's a boolean. So we go to the components and has no key, contains key. We check if no is not enough. because you want to get to the bucket for the type T and to check in the corresponding cell of the entity ID if we have none or a value there. So for this one, let's steal some code. Let's steal some code from here. From this one. Do we need to treat? No, let's steal that code. And go ahead. Okay, we need this type ID. I'll just delete, copy, paste, save, type ID, yada yada. Next. Let's delete that. So at this moment, we have our type ID. We get the bucket for that type. And we also, if we can't retrieve the bucket, so if we can't retrieve the bucket, we return false. Okay. But if we retrieve the bucket, if we retrieve the bucket, we go to bucket of entity ID is sum, and that's everything we need. But we don't like something. If may be missing an else clause. Ooh. Yeah? Yes. Let's read it again. So, we don't need this else. By default, we will return false. Okay. Now, if we return sum, if we did not find the bucket, we return false. Expected what is sum? Found bool. Expected is to be considered. Okay, let's rewrite it. Let's rewrite it because I don't know what's wrong. Okay, so for this one. Okay, let's rewrite it. So by default we return false. The first thing we want to do is to get the bucket for T. Okay. So to do that, we go to our components and get, and we get our bucket for type ID. And then after we got our bucket, So after we got our bucket, we want to downcast it. So we want to do bucket dot down any as any, and so we cast it to any, and then at our bucket we let's just downcast it directly from here. So downcast ref, because we just want to read some info. And to downcast it to a vec optional t. Okay, that's all. Okay, let me make some sense of this. Bucket sum. Now it's better to just do it in small increments. Okay. Then with this bucket we do downcast ref, and as I said, a vector of optional t. But still you don't like something. Hold on. Okay. Which one to do? Semicolon. And then with our bucket, what do we want with our bucket? With our bucket, that's an optional. Yes, because the cast might fail. Bucket.map bucket. With our bucket, so the map function returns an optional. Okay, I try to be smart, but I'm not that smart. So let bucket equals that, but no. If let bucket. So if we have a bucket, I don't know why I overcomplicate things. Let's just copy that. So if the bucket exists, If the bucket exists, we get the concrete implementation of the bucket. And we want to ask, is some. Is it or is it not? Actually, we return this. We return that. Okay. If we don't find the bucket, we just return false. And that's it, I guess. What? Consider iterating over a slice. Okay. And let's remove this. Hash map, okay. Let's check the tests. It failed. Nice, what can I say? Why are you failing? Did I do the add? Bugger. Let's debug this test. Command rest analyzer failed, reason unknown, request. What? Rest analyzer debug test. So, no, Rust enhance is the plugin for Sublime I'm using. Rust enhance the bug test. Okay. Sublime text. Okay, I see here something. So Rust analyzer Emacs Sublime. Okay. We need to restart debug. Okay, it's not what I want. Coming back to this. Object. I don't have GDB. Yes, I have it. I try to debug it instead of going line by line. To do debug dbg and that. I like this macro. Manifest. Okay, let's also go with debug. What else? We need to require T2 be default constructible and implement debug. Debug. That trait does not implement debug. Is not implemented for. Okay, and what can I do with you? Delegate, yada yada, nothing useful. No. What if I do implement debug for this one box the component bucket rate? I have that and not derive macrogeneric. I don't get it. Anyway, go away. Okay, we can do that. But what can we do? We can do that. So let's place those debug macros somewhere else. Let's inspect that component. Maybe we go wrong here. So what about doing debug bucket? Yeah, what about that? P doesn't implement debug. Okay, debug. We require our T's to implement debug. Consider importing one of those items instead. Core format debug or standard format debug. Well, I'll go with this one. place qualified pathway to use. Yes, that's what I want. Okay, borrow. Okay. Okay, let's check that out. Failure. It did not print anything. So yes, it did not went this way because the bucket does not exist at this point. So we are here in this case. Okay, so bucket. Okay, can add object entity. So the bucket is empty. Yes. It is empty. Oh shoot. I know what's going on. So here we reserve the capacity. So we reserve the capacity, but we did not. One more thing to check to move that bug check there. After we set the component for the entity. Okay, where are you? Here. Okay, here. Okay, so what do we have here? Okay, so we get the panic because the index is out of bounds. Yes, my friend. So, with capacity, with maybe we have another type of constructor from either from parts from parts, no, from either, no, from extend, from slice. No, I'll just do those stupid things so I have the capacity, and because I have the capacity I will just do for something in 0 capacity range. Capacity not included. We will do bucket dot push none. Okay, we do that. Oh, and only after that we set the right cell for our entity ID to an instance of the component. Okay, let's check that out. Boom, that was it. Okay. But dbg. Okay, let me remove those debug. Okay. I think we need to refine our test a little bit because you saw we need to consider this. Are we adding a component to an existing bucket or not? So we need more specialized tests. Don't crash when removing an entity. Okay, can add simple component to entity for first time. And in this case, yes, we have our universe, we create an entity, and we add a component, whatever the type. But this is the first time we add a component to an entity. Then we do another test derived from this one. that goes like this. Can add the simple component to entity for second time. So you have our universe, you have our entity, we add a component of type useSize, and this time we will add another component of type float32, and we will do those assets for those components. And similarly for this one, add so let's rename it. So add object component to entity for first time, but no. So add to components. Let's rewrite those tests. Okay. Sometimes it's just best to start from scratch. Can add component. Actually, don't care if it's a simple or a struct. So we can add component for the first time. And we have a mutable universe default, and add component to entity. We want to check the first time, so we have an universe without changes. We add an entity to it. We add an entity to it, and that entity has no components. So because it has no components, we have no buckets defined. That's what I mean for first time. For first entity, because once we add to the first entity in our universe, it should be also defined but not initialized for the second, third entities. So can add component to first entity. Okay, to first entity. Let's create the entity, and we have universe.create entity, and then universe.add component, and we'll use as usual our friend useSize. Now we've added this entity, this component to this entity. Now we want to accept that we have the component of this entity, the component of this type for this entity. So can add component to first entity, and then we want to check that can add component to second entity. So we create for first entity, the second entity, we add the component to the second entity, and then we ask if we have an entity for, and of course we don't care about this one, second entity. even now, until we execute this line, no buckets are created. Can add component to first entity. A component to first entity, can add component to the second entity, and let's go with a float 32 here. If we vary it like this, we will test that we actually can add component to first entity. Now can add component to single entity. To single entity, then can add components to two entities. And yes, we want that, and we add the same component, and we assert for both entities. Let's check now. Okay, everything works. Can add the same component to two entities. Okay, and another test derived from this one, where we can add different components to two entities. So yes, let's delete this one. The first one is a new size component. And another scenario we want to cover is can add different components to the same entity. So we create the entity in our universe, and we add both a new size component and a float 32 component to this entity. Okay, let's check the tests again to see if we have overlapping. So can add component to single entity. So a component can add same component to not two but multiple entities. And actually, just to be sure, I will go with more than two. I have this idea that if it works for 3, it will work for n. If it works for 1, yeah, it's just my mind. Okay, so we have that. Same here, when we can add different components to multiple entities. Okay, so we have multiple entities. And this one will be, let's go with an unsigned 32 that we will add to the third entity, and we will check if we got that unsigned 32. We can add different components, multiple entities. Okay, can add different components to the same entity. Yeah, that. Okay, let's check that out. Ooh, something failed. So which scenario can add different components to multiple entities? So this one failed. This one failed. Why did you fail? Mm, let me guess, it failed. Mm, it let's see on which part of those two. So at which well, it failed at line 171. 171. Yeah. Ooh, nice. It's actually it's good. It's okay because the test was wrong. The test was wrong. We were checking if entity 2, if entity 2 had a component of type U32, and no, we set it to, okay, so our test was to blame. Okay, save, and let's check again. Okay, now we are covered. Let's go back to the user story. So each component type should be placed in its own memory continuous bucket. We are doing that. We are doing that because of this. You see, when we add a component, if it's not there, if it's not registered in our hash map, we create here we create a vector of optional t's. So this vector is continuous. Nice. What else? So this is done. When an entity is removed, the corresponding components are removed. Ooh. Okay. Let's write a test. Can so we create a universe, we create an entity in the universe, we add a component, and then we remove the entity. We remove the entity. I think this is quite tricky. Let's go to the drawing board. So let's say we have this entity 3 entity, okay? When we remove it, we also remove it from the entity container. So we remove it from here. Now we put those in none state. Okay. So we have this column. We have this column set to none variants. We have nothing there. But because we removed this entity, when we create a new entity, we'll add stuff here at the end. So when we create a new entity, we add stuff here. But this will remain like So it will be nice and efficient that yes, when we remove an entity, those chunks in the bucket are initialized to none values. That's okay. But when we create a new entity, we would like to reuse this memory, because otherwise, yeah. So I think I'll introduce the idea of an entity record. An entity record that will actually let's so the idea of an entity record. So this will be a struct basically, in a way or another. So we have this this struct, and here we will have an index that will be a new size. This is for sure a new size, it's not debatable. Why? Because this index here will, so we will get this and index our buckets, you know. So based on this index, we will go and index our component buckets. Okay, and in this way we will reuse parts of memory when we delete an entity, and at the same time the entity ID will be unique and always incrementing, but the actual physical place in the bucket will not be described by this entity ID, it will be described by this entity record. Ooh. So let's implement this. This turns to be quite long, isn't it? Okay, let's define this test for an entity removal. So can remove entity, let's write this and we will see then if we need to cover other cases. So we will steal this, we create a universe, create an entity, we add a component to the entity. Let's add two. Okay, so let's have this. So at this point we will have an entity. Oh, I was pointing to the main screen, not to the graphic driver. So at this point we'll have an entity and we'll have two buckets for it. Okay, so what we might do for test, of course we will remove the component. remove the component F32 from the entity, and yeah, we remove both components. And now we need to somehow check that that we have nothing defined here in those cells, and also that our entity is no longer in the entity buffer tracker, how we want to name it. So we'll accept that the universe will. So the answer to this question, does the universe have component of type uses for the entity and F32? So if this returns false, if that returns false, it means that this is not sum, it's none. So it's okay. So let's go back. And well, you know what? Can remove entity. Well, can remove entity? I think we already have a test for that. Can remove existing entity. Okay. So can remove components from entity. Okay, with this test, the entity will still remain alive after we remove the components. And there is another scenario when we remove the so can remove components from entity. And just to cover our basis, we will create two entities. And those two entities, what they'll do, they'll have their components. We remove the components from those two entities. And yes, why I do this? Because I also want to check that we will have after we remove those components once from the first entity and from the second entity, we are in this case where for the first component type this will be none, and this will be none for the second entity, for the second component type. And now this is the tricky part, because can remove entity and its and attached components. Okay. So for this scenario, we'll do this. Well, not really, because you know what? If we remove the entity, we will no longer be able to query the universe that we have or no longer have particular component type for that entity. Honestly, I don't know how to cover this scenario. I don't really know. Okay, so the action is this. Add component to the same entity, and we don't remove the component, we remove the entity. Let's see a little bit the other test for entity removal. Remove existing entity. Yes, we don't deal with components here. So this test is legit, it's not a duplication. So we remove the entity. We remove the entity. You know what? I know I'm not dealing yet with what I described here as the entity record. No, I just want to cover this one for now. Let's drink some water. Remove the entity. But because we remove the entity, we can no longer interrogate if we have components for that entity. So entity remove entity contains. So I think a better thing to ask ourselves is that if to ask if the universe contains the entity. So we will do like this. Universe contains entity. We don't need a type here, and we have our entity. So if the answer is false to this, then the removal worked. How did I do it here? Not that. Can we? Entity exists. Entity exists. I don't like that name. I'll go with contains and name contains entity. So let's use that here too. So at this point, if the universe does not contain the entity, it is perfect. Remove entity. Yeah, and this is the bad thing, that I can't query at this point the universe to check if the components were removed. But I think I have a scenario in mind. Let's finish the implementation for what's missing here. So we are missing this remove component function. We will add it here under the component public function remove component. Yes, we'll get a mutable reference to self. And yes, we will also get this stuff here, the generic type. Now let's think a little. We need that, not there, here. What did I do? I don't know. So we have our type ID. What should happen when we try to remove a component that's not attached? It shouldn't fail. So because of that, can remove entity and attached components. Then can remove components from entity. And another scenario is the no crash when removing non-attached components. Let's do this quickly. So our entity, our components, and we don't do remove entity, we do remove component. But instead of type usize or F32, we'll just go and try to remove an signed 32. And we don't. Yes, here we can assert that we still have those components set. Has component of type. It's good to make sure that we still have them, meaning that this call did not affect the layout of our buckets in some way. F32, not 23. Remove component of type that. Okay, so we have this function, and yes, we also require an entity ID as our parameter. Sorry for jumping back and forth between the test and the implementation. Maybe I can do something like this. Yes, I can do that. I also open not application but ECS-lib.rs, this one, and on top I'll be on the implementation part, and here I'll be at the tests. No crash when removing non-attached components. I'll rename to this can keep memory integrity when removing non-attached components. And I'll go even further, and I'll have this being the first entity. I'll create another entity with some with the same components as the first entity, but I also add assign 32, and I'm asserting that everything is okay for the first entity, and also I'll be asserting that We still have the U size and the F32 and the I32 for the second entity. Okay, and here let's go to how was it called? Remove component. Okay, so if we don't have a bucket, we don't care. So if let's some self that components, not that, come on, components. I don't know what's going on here. Isn't this a hash map? I don't know. Okay, let's just write the code. So we go with a has key. No, something is weird. Has key. Self.components contains. This is exactly what I want to write. What's going on? So if the components, you know what? I saw something else here for has components. Why should I check the key? I get this. And if I took some reference to the of the key, and it's an optional. So if this returns none, it means it don't contain the key. So we get rid of that check. Okay, but we still have something weird going on with this one. Like if it's okay, I don't know what happened earlier there, so we'll do the same. If let us bucket, we have some bucket and we want to be mutable. Okay, so we get the bucket for the type T. And actually I want that in here. So I get the bucket, then I get the concrete bucket for the actual type D, and I want it to be mutable, and don't cast mutable, and I just want to set it to none because I'm removing the component. None. Oh, come on, none of this entity ID. Remove component. Okay, let's check that out. Okay, so now we have those scenarios. Now let's go to the final part of this devlog, where we implement this idea of entity record so we can reuse space after we remove components. So one idea I have in mind is something like this. Okay, we have our universe, we create 3 entities like we have here. So we create those three entities. Then I remove entity number 2. So this part will be set to none. And then I'll create a fourth entity. I'll get a fourth entity, and somehow I want to check that we are reusing what we set to none here. To be honest, I don't really know how to assert for that. Let's write the test. And actually, I think I know how. I do like this. So we are at the stage where we created the entities. We add components with specific values, not with default values. Okay, and we will use the fourth entity to query about its components. First, we will make sure that we contain the components we have the components we set for the fourth entity, and at the same time we shouldn't crash, because even if the fourth entity has ID 4, it will actually index here the second column of our component storage. Okay, maybe in code it will make more sense. So let's write the test. No crash when indexing can reuse storage space from deleted entity and okay, I think this is clear enough. Okay, so let's get our scenario. So we have our universe. We create three entities. We set we add a component 3 times. We add a new size to all of them. We add we add an F32 only to the first entity. And we'll add to the second and the third entity not float 32 but non-signed 32. At this moment our layout should look something like this. So I have the first entity, the second entity, the third entity, and we have use size as a bucket. We have float 32 as a bucket, and we have, I think it was an unsigned. Yes, an unsigned 32. Unsigned 32. And what we said that, not there, here, we said that we added all the use size for all of them. So we have use size for all of them. Then F32 we have for the first entity. Okay, so we have F32 here for the first entity. And what next? Unsigned 32 we have for the second and third. So we have unsigned 32 here and here. And what I'm proposing is to also add F32 for the third entity. No, not that, but here to the second entity. So we add a float 32 to the second entity. Okay, second entity, and then what we do, we remove this, we remove that. We remove that. Okay. Okay, for that we do a universe to remove entity, and we remove entity number 2, and after that we create a new entity. So let entity number 4 equal universe to create entity. And for this one considering that we will reuse this storage space, I want to set only the F32. I want to set only this one. Okay, so back to this one. Add component F32, this entity. Not entity 3, entity 4. And now we are accepting that universe that entity contains entity returns false for entity number 2. Then what else do we accept? We accept that it keeps the memory integrity for entity number 1. So we check that entity number 1 has a usize in F32 set. As component entity 1. Okay. Usize and an F32. And for entity 3, the usize and the unsigned. The third entity, float and the unsigned 32. What else? That the fourth entity that now is in place, the fourth entity does not have usize set. It has F32 set and it does not have U32 set. So 1, 2, 3. Entity 4. It does not have the usize set, but it has the F32 set. And those are actually this way. Okay. Let's see if I broke something. Panicked. Panicked line 274 at this line. So here what I'm doing, I'm checking if entity number 3 has F32 set. Ooh, no. Actually, you know what? Here, when I'll check the integrity, I'll check for the 3 types. The usize, the F32, and the unsigned 32 for the first entity, of course, but the first entity must not contain the unsigned 32. Okay. This number 2. Well, we no longer have entity number 2. It's actually number 3. For entity number 3, we check that the float does not exist. Okay. And for the entity number 4, we check that only the float exists. Now there might be an argument about checking if actual values are So let's consider this. After I created the second entity here and after I added the component to it, yeah, I changed the component. Okay, let's check that out. Okay, it fails. Deleted. Okay, let's refactor this so then we will actually have an entity. Okay, that is a struct with public no, private field called record. Entity, I call it entity record, right? Yes, entity record. So this is entity record. You know what, actually? The entity ID. No. The entity ID remains like that. And we go to our universe. So we have this next entity ID, entities, and those entities are actually a hash map from oh, this is hard. A hash map from an entity ID, the thing that's unique, to a new size. Entity. No, I'll just go like this, records. Entity ID to index. So bucket index. Oh, damn it, I prefer to be verbose and understand what's actually in there. So we have our entity ID mapped to an actual index. Let's define the index similar with how we defined the entity ID index. Okay, color components. Okay, let's review this. So when we create an entity, we have our entity ID to bucket index. So when we first create the entity, we want to go and see which column we want to check if our entity ID exists in the mapping. If it exists, then so if we have a mapping, does it make sense? So if this ID exists here, no, 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 no. Oh, for this one, so we want to get from an entity ID that's unique and incrementing. We want to get to a particular index in the sorry, to a particular index in the buckets. So if this entity or we should have it the other way around, from an index to an entity ID. No, 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 no. From an entity ID to an index. Let's see what index. So for the existing entity IDs, for the existing entity IDs, actually we get all the keys, so all the entity IDs. No, 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 no. Actually, we will go sad. Okay, I have to be honest with you. Let's end the discussion here. I need to take a longer break to go have a walk. So this will be the first part of our journey of implementing ECS. And yes, because of this, a lot of those user stories will be transferred to the second sprint. But at least I'm happy that we actually, I think we implemented quite a few things we implemented. So before I end the first part, let's review a little bit. Let's review a little bit and let's comment for the moment this test that's giving us headaches. Let's comment that, and it is, and let's return to entities. Those were a vector of entity IDs, if I remember correctly. Yes, we have some dead code there. Let's comment it out. We will need it. So, okay, so what we implemented so far, besides this last scenario, it's fine. Now, let's take a look over our user stories and see what we implemented and what we did not. For this one, we'll have it open here. So each component type should be placed in its own memory continuous bucket. When an entity is removed, the corresponding components are also removed. So we covered this. Okay, so we covered that. We covered that. Let's and I worked here directly on develop. Okay, either way, doesn't matter. Let me delete that branch. Okay, so let me stage first everything. So let's draft a commit message. So this one closes number 7. Okay, number 7. And this one is about add plain data object as components. Okay. Next. Okay, this one. Retrieve a component from an entity. So we can retrieve a component from the entity. We can mutate the component from the entity. I think we did not cover this. No, we did not cover this. So this is not covered. Query, yes. Yes, we only took care of, oopsie. That's my recording studio. So add plain data objects to components. Okay. Well, add remove engine ECS. Add and remove plain data objects as components from entity. And this one closes number 7. Where are you? But this one closes this one, not this one, this one. But it's actually partially implemented because of that stuff with. Yeah, let's end here. I'll consider this one implemented because we are actually adding components and removing them. The removal might not be efficient because we are remaining with unused columns in the bucket matrix, but I can sort that in the future. Okay, so thank you for watching. If you enjoyed this long devlog, like, subscribe, and see you next time. Bye bye.